For more detail for this case, that's we change the number also from the example for this assignment. Okay, so actually you may study it by yourself for the clip video that I already given for you. Okay, but this is just a little bit in detail. We know the part that the part equation is become r equal to 2rc cosine theta. Okay, and if the arm has the angular velocity omega, that is or maybe defined like the theta dot equal to 0.2 radian per second. Okay, and the angular acceleration theta dot equal to 0.4 radian per second square now. And we would like to consider at the instant of theta equal to 30 degrees. We would like to find the force of the arm on the ball, and we neglect the friction and the size of the ball. Okay, we neglect the size of the ball means that we consider the ball as a particle, and we know that RC is become 0.4 foot. Okay, and the ball has a mass of has a weight of 0.5 pounds. Okay, and from this we know we know the motion like this, and for this case we should apply the polar coordinate system to solve this problem, because the part is defined in theta direction, in theta coordinate. So it may be better to form the equation of motion in and theta coordinate system. Okay, actually you may solve this problem in xy or in normal and tangent like the previous one, that's last week that we considered just only kinematics. Okay, for the case that if we know the part, maybe better to apply the normal and tangential coordinate system instead of xy coordinate system. And for this case, r theta is maybe better because we know the part that's in terms of r in theta. Okay, so for this case, because we will solve in r theta direction. Okay, so then we have to take the first derivative of r, okay, and second derivative of r. Okay, so for the first derivative of r, we have our function and 2 and rc is constant. So then we obtain this one. Do not forget the chain rule. Okay, we take the first derivative of cosine theta here, and with the first derivative of cosine theta is become minus sine theta, right? Okay, and do not get the chain rule. We have to take the derivative to the theta again, theta dot. Okay, and this is the mistake of student. That's always happen. That is when we take the second derivative to to r. That is take the first derivative to r dot. You see that we have to term now in terms of two functions of theta, that is sine theta and theta dot. Okay, so then we have to apply the derivative of a product of two functions, that is equal to duv by dx equal to udv by dx plus v du by dx now. And for this case, we have this term. Okay, normally my student always just has just only one term. That is they forgot to take the products of two functions. Okay, so now we have r dot and r double dot formula, and we have to consider the free body diagram here. Okay, and for this problem, I give you the additional pictures for the case of free body diagram. Okay. So we have the ball here, and the contact surface is we have two contact surface, that is the contact from the arm that we have NOA here. Okay. Okay. So if I draw, if I zoom this part, we have NOA. Okay, and from the contact surface that is about the circular part, the semicircular part here. We should have the normal force here that is perpendicular to the part, that is NS. Okay. So if we consider the angle from this picture, we found out this is RC, right? And this also RC. So then if the arm moving with theta, so then this should be theta also. Okay. And from the triangle, we found out this should be 180 minus 2 theta, right? Okay. So then we obtain this angle should be 2 theta. Okay. So for the projection, when we consider the mg, the force, mg here, okay. Actually, this picture is actually this one is the free body diagram, but it's not. It give us nothing because it has no information about the angle to decompose the force in r and in theta direction, right? Okay. So for r direction, we have here. This is r direction. Okay. And this is theta direction. Sorry. It should be perpendicular to normal. And this is r direction. And this is theta direction. Okay. To decompose mg to theta and r, we would like to find this angle, right? Okay, but we already know this should be theta. Okay, and from the projection of this line, okay, we know that this should be 90 minus 2 theta, right? Because we already know this is 2 theta. If we consider this angle, this triangle, this is 90 degree, this is 2 theta. So then this should be 90 minus 2 theta, right? Okay. And in the same manner of this, okay, because this is the angle, so then the angle of this is become 90 minus theta, right? Okay, so then it's mean that this angle should be theta also. Okay, that's why we have the free body diagram here. Okay. And for this case, MA theta and MAL. Okay, from the free body diagram and kinetic diagram. Okay, we before we consider the equation of motion, we just come back to kinematics first. Okay, from the first derivative of R term, okay, we have R dot become minus 0.08 for this case, and for R double dot, okay, we determine that is equal to minus 0.188 foot per second squared. According to this value, we can find AI and A theta here. And AI A theta become minus 0.2157, okay, and 0.2452 foot per second squared. Okay, we have two components now. And we back to consider the equation of motion in R and in theta direction again. Okay, substitute each value that we already determined to the equation. We can solve for normal force in NS and the normal force OA. Okay, in S and in OA, that is become 0.2808 pounds and 0.29 pounds respectively. Okay, so that's complete this problem.